So today we have the last two talks in this seminar series. The first is Zhouli Xu, who will tell us about the existence of data 6.
Thank you for the introduction. So I'd like to first thank the Isaac Newton Institute and the organizers for this opportunity for me to speak here. It has always been a pleasure to visit here. So I'd like to talk about the joint work with Weinan Lin and Guojun Wang. So they're both at Fudan University now on the proof of the existence of theta 6. So I'd like to give an overview of the ingredients of the proof, especially some of the ad hoc part of the argument, and also a little bit of future directions. So the theorem is that the element H6 squared survives to the infinity page in the Adams spectral sequence. So due to a theorem of Browder, that implies that there exist free manifolds with covariant invariant 1 in dimension 126. So together with theorems of Browder in the 60s, Mahawar-Tangara in the 60s, Barrett-Jones-Mahawar in the 80s, and more recently Hill-Hawkins-Ravenel, that means that free manifolds with covariant invariant 1 exist in and only in dimensions of these 6 dimensions. So the connection between free manifolds and this element Hj squared in the Adams spectral sequence was established by Browder. So in particular, Browder proved that other than dimensions 2 less than the power of 2, other dimensions there's no free manifolds with covariant invariant 1. Follow from the existence of these Hopf maps. So it's not hard to see that in dimension 2, 6, and 14, there are manifolds with covariant invariant 1. And the dimension 30 case was established by Mahawar-Tangara. Dimension 62 case was established by Barrett-Jones-Mahawar. And Hill-Hawkins-Ravenel proved that the later dimensions, starting from 254, there are the elements H7 squared and later ones, they do not survive in the Adams spectral sequence. And therefore, there's no manifolds of covariant invariant 1 in higher dimensions. So this theorem today is more about this specific last case 126. So I'd like to comment that this covariant invariant defined on smooth, stably free manifolds is actually a group homomorphism from the homotopy groups of spheres, the stable ones, the co-kernel of J to the group Z-mod 2 is a group homomorphism. So that means if there is a manifold of covariant invariant 1 in one dimension, then up to framed cobordism, precisely half of the manifolds in that dimension have covariant 1, and the other half have covariant invariant 0. So the dimension 30, we do know an explicit manifold by John Jones in the 70s, but in dimensions 62 and 126, the arguments are homotopy theoretical, so we still do not know any explicit manifold in these two dimensions, although half of the manifolds in these dimensions are supposed to have covariant invariant 1. So that's something we should be able to figure out, hopefully soon. But all right. So for the ingredient of proof, so Weinan Lin is the programmer of this project. So who made computer program to compute various things for the Adams spectral sequence. So the first thing he did is using the theory of non-commutative Grobner basis, you can compute X over the Steenwald algebra. There has been many very useful, effective algorithms and computer programs computing the X over the Steenwald algebra, which is the E2 page of the Adams spectral sequence. So we then also made a program which is, in my opinion, very fast, very effective. In the normal range, it computes not only the additive structure, but also the product structure. In the normal range, it matched perfectly with say, Brunner's program and NASA's program, etc. But Weinan's program can also be used to compute other modules, and moreover, maps among these modules, the induced maps on the Adams E2 page. There are a few other things that Weinan's program can do. I'll mention that in a second. So there's also a recent theory of secondary Steenwald algebras. So when some primary operations vanishes, we can define a secondary Steenwald operation using total brackets. So work of Baus, Giblet, and also later NASA, they formed the theory of secondary Steenwald algebra. So its homology is the E3 page of the Adams spectral sequence. So in other words, one can read off D2 differentials, all D2 differentials, by knowing the secondary stimuli algebra. So in fact, Tra has made computer programs to compute all D2 differential in a big range using the theory of a secondary stimuli algebra. So Wei-Nan has also done that, but for applied for various other modules. So another thing Wei-Nan's program can do is his program can propagate differentials and extensions. So if we have a few known differentials, we can use, say, the Leibniz rule to obtain newer differentials. And we can also use naturality to produce new differentials. So Wei-Nan has a, excuse me, a web page. So in the current archive version, we involved 49 modules spectrum. Most of them are finite. And we study, so for each of them, so this is the sphere, that's TMF. So that's information a lot are known. There are like cofiber of the Hopf maps, some 3-cell complexes, and some 4-cell complexes, and some subquotients of RP infinity. If you just click on any one of them, there is the corresponding atom spiral sequence picture for the corresponding module with a lot of differentials that are already computed. So the way to compute this is we use the secondary stimuli algebra to produce a lot of D2 differentials, all these modules, but we also use naturality to propagate them. So for example, we also study cofiber sequences. Say, for example, this one is between the mod to Moore spectrum. So that's a page with all the inputs are all the infinity page of the 3 spectrum. And then we can study how the maps among them as D0, D1, and higher differentials. So this spiral sequence converges to nothing, converges to 0. We can also do this on the X. So for example, if we take this map, would be the quotient map from the mod 2 Moore spectrum to the sphere. So if I zoom in, you see on the page, the two sides are, the left-hand side is the top cell, the sphere in dimension 0, I guess dimension 1 after shift. The right-hand side is the mod 2 Moore spectrum. We can move these columns here, and there's a line denoting like which dot comes from either the top cell or the bottom cell. So that has also been calculated, all the maps on the E2 pages. So therefore, whenever we have some differentials, we can also use naturality to do that. So there are more subtle things we call the generalized Leibniz rule and the generalized Mahauer trick. I'll get to that in a second. So basically, Wei-Nan's program can do a lot of these computations and give us a lot of differentials coming from the D2s and naturality. So the problem about 126 is for the sphere. It's specifically for this dot. The name is H6 squared. So by the way, the fact that when you click on a dot, you can see the name and some relevant data was done by Chartan. And so we now also use that part in this program, so you can actually visualize a lot of the information on the web page. As you can see, the computer program doesn't tell us it is a Perm cycle. It tells us the sum of this is question mark. But anyways, so the problem is, does this dot survive? Is that a permanent cycle? So in STEM 125, there are 105 dots. So these are the potential targets. So if this one supports a differential, it could hit any one of the, or some linear combination if they are in the same filtration. So using these naturality and big data, so to speak, a lot of like modules and naturality, together with something called the Barrow-Jones-Mahauer's inductive approach, we can get rid of 101 out of this 105 dots. So they're not going to be the target of the differential supporting by H6 squared. So there are 4 remaining. Then we have to establish some newer theoretical methodology. So these are some techniques coming from the HF2 synthetic or filtered spectrum. So we developed something called generalized Leibniz rule and generalized Mahauer trick. So by combining these tricks, we can put into the computer program to produce more differentials. Together with this inductive approach, we can get rid of 3 more dots. So there's only 1 left. So the remaining one, we have to use some ad hoc arguments, which is a little bit lengthy, but not too bad. So that's something I also like to talk about today. So basically, before Hugh Hopkins-Ravnow's result, there was some inductive approach trying to establish all the theta j's. So it could be possible that all of them survives, right? So there are free manifolds in all dimensions later on. So that's the Barrett-Jones-Mahor's inductive approach. So if we know one theta j exists and has order 2, whose square is 0, then the next one exists and has order 2. So you can try to inductively establish all of them. But now we know it has to break down somewhere, okay? So we can upgrade this inductive approach specifically just to the fate of theta 6. So work with Birkeland in the context of HF2 synthetic or filter spectrum. We can show that so theta 6 exists if and only if this relation is 0. So theta 5 is the element in dimension 62. So eta is the first half map. Lambda is a parameter in this HF2 synthetic spectrum, also a homotopy class. So if this relation is 0, so this is essentially the non-homotopy. It's something supposed to be killed, suppose theta 6 should kill, but if it's already 0, then theta 6 is a permanent cycle. So then we have to use whatever the computer program tells us, the remaining data in this picture. There's still many differences we couldn't really compute. Like this one, for example, we couldn't compute D6, but we know D2 until D5 are all 0. But there are some we do know is the information. So for using the remaining information and some ad hoc arguments, we can actually prove that this relation is 0, and therefore conclude that theta 6 exists. So that's basically the strategy of our proof. So next, I'd like to talk about this technique and some background regarding HF2 synthetic spectrum. Any questions so far? All right. So for some background, I'd like to first mention multiplic homotopy theory because that's the motivation of this synthetic spectrum. So let me denote by SHC to be the multiplic stable homotopy category over C. So one important feature of this category is that there are bigraded spheres. So therefore, all the homotopy groups and the homology groups are all bigraded. So there is a particular map. The name is tau in degree 0, -1 between the completed spheres. It has an important property that Zhouli proved that so just like the classical cohomology theory is represented, it's represented by this MAPI Allenberg-MacLane spectrum in the multiplic setting. So its bigraded homotopy groups is FP adding tau. So this tau as a map between spheres is detected by homology. And this whole homology point is a one generator polynomial algebra with tau.
Can you say what's the hat?
Hat is just the completed. It's completed of HF2, HFP. So this tau does not exist between uncompleted spheres somehow. So the specialty of C is that over C, if we take, there's this Betti realization functor from SHC to SH, the classical stable homotopy category. If you take a complex algebraic variety and take the C points, you get a topological space. You can extend this construction to the entire category. And in particular, there's a functor like this. It sends the bigraded spheres by ignoring the second grading. It sends the FP multiplic Allenberg-MacLane spectrum to the classical one, and it also sends this tau to the identity map. So basically, classically we use Adams-Novikov spectral sequence to compute the classical homotopy groups of spheres. So multiplically, we can use the multiplic analogs like the ones based on HFP or the multiplic version of mu or BP to establish the multiplic Adams and Adams-Novikov spectral sequence. So people have studied these spectral sequences. So one observation, one thing I think is really important and very interesting is that the multiplic Adams-Novikov spectral sequence is rigid in the following sense. So it is isomorphic to a Bachstein spectral sequence parameterized by this element tau. So what it means is that the multiplic Adams-Novikov spectral sequence, the E2 page, is nothing but the classical one, but adding this free polynomial generator tau. Okay, and moreover, the pattern of differentials, it is completely decided by the classical Adams-Novikov spectral sequence. So if we have a D2R plus 1 differential, then in the classical one, that X kills Y. So by sparseness, these are the only non-zero differentials of odd lengths. Then there's a corresponding non-zero differential in the motivic setting by decorating it with the power of tau. And the power here is determined by the length of the differential. So in this sense, these two spiral sequences, they determine each other. If I have the motivic information, I just invert tau, letting tau equals to 1, I get the classical information. But the classical one also completely determines the motivic one. So that's why I call this a rigidity property. So now, if we consider the cofiber of tau, it's a two-cell complex. Okay, Gregory proved that this is actually an infinity ring spectrum. Its motivic Adams-Novikov spiral sequence actually collapses as E2 page. Right, the E2 page is just modeling out by tau, and all differentials should have a tau, and there's no tau anymore, so there's no differentials at all. So therefore, this two-cell complex is homotopy groups. It's just the classical Adams-Novikov E2 page, okay, which is something completely determined by homological algebra. So there is a theoretical understanding of what's going on here. So if we start with cellular modules over the completed sphere in the motivic setting, we can invert tau. So Duggar and Isaacson proved that this gives us the entire category is the classical stable homotopy category, complete at prime p. And if we mod out by tau, namely we consider modules over this infinity ring, cofiber tau, then this is so Gregory, Wang, and myself, we proved that this is equivalent to the derived category of BP star BP comodules in the sense of Hobby. And so if you think this element tau as some kind of parameter, so inverting this tau gives us a generic fiber, that's the classical information. And the special fiber is something purely algebraic. It's the derived category of a well-known abelian category. So having this deformation of categories give us very useful tools in computations because we can also have deformation of spectral sequences, right? So we can consider Adams spiral sequences in these three categories. And the middle one is the motivic Adams spiral sequence for the motivic sphere. The left-hand side one is the classical Adams spiral sequence for the classical sphere, and there's inverting tau gives us a map of spiral sequences. And similarly, mod out by tau on the right-hand side, that's isomorphic to something called algebraic Novikov spiral sequence converging to this X group, which is completely algebraic. You can even make a computer program. So indeed, Gordon actually have a computer program to compute this effectively in a large range, like over 100 stems. And then all the differentials on the right-hand side, it's a motivic Adams spiral sequence, right? So we can use naturality to pull back to get differentials for the motivic sphere. But the input, these differentials are like for free. Then we get a lot of differentials in the middle, and we push back to the classical one. So using this method, Isaacson, Wang, and myself, we can extend classical computations from as a prime 2 from dimension 60 to about dimension 90, but not yet to 126. All right, so having this background in mind, so Piotrowski introduced to us something called the synthetic spectrum. So I'm going to specialize to the case that it's based over a theory E, where E is HFP. So this is the stable homotopy category of synthetic HFP spectrum. So just like the motivic case, there are bigraded spheres, and there is a map in degree 0, -1 between the spheres. So I'm to make a distinction, I'm going to call this parameter lambda. And the homology of a point is FP adding lambda as a one-generator polynomial algebra. And there's also a deformation picture. So this time, if we invert lambda, then we get back to the classical stable homotopy category. But when we mod out by lambda, since it's based over HFP, this is the derived category of the classical comodules over the Stingwald algebra. So it's something also well known. Okay, so when we restrict attention not to HFP but to BP, so the synthetic BT spectrum is just the same as a theorem due to Piotrowski, the C motivic cellular spectrum, and now it can be generalized to other spectrum. And Gregory, Axon, Cross, and Ricca proved that they define something called filter spectrum, also based on BP. So these constructions are all equivalent, giving us the same category, which also realize the C motivic cellular ones. Okay. So So the multivic one, the Novikov one is rigid, and synthetically the atom spare sequence is rigid. So later on, it's going to refer the multivic one as the C-multivic one, and the synthetic one means the HIP synthetic one. So the synthetic atom spare sequence is rigid. Okay, so what do I mean? So again, it's a Box-Stein spare sequence parameterized by this parameter lambda. So it's synthetic atoms E2 page converging to the synthetic bigraded homotopy groups of spheres has the E2 page, where the E2 page is the classical one, adding lambda as a free generator. And there's a map by inverting lambda. Okay, and again, the pattern of differentials, they determine each other. So if you have a non-zero classical atoms differential, then there's a corresponding synthetic one decorated by a lambda power. Okay, and we can also consider the cofiber lambda. Then the synthetic atoms collapses at E2 page because there's no lambda anymore, and all differentials are 0. So therefore, the homotopy groups is the same as the classical X over the Steenwald algebra, like that. And but we can also consider not just the synthetic sphere and the cofiber lambda. We can also consider cofiber of lambda to the n. These two cell complexes in between. So they should encode some information about En plus 1 page. So it turns out this interpretation is very useful. So for example, classically, when we talk about non-trivial extensions among two elements, they're usually for elements on E infinite page. They have to survive the spiral sequence, right? Then they correspond to homotopy class, and we can talk about extension problem. But if they were both killed by some elements or even support the differential, then it's hard to give a rigorous argument to mean what do I mean by having an extension. Of course, there are ways to do it, but synthetically it gives us one way to do it, namely they correspond to elements of actually bigraded homotopy classes. Then we can talk about naturality and maps and connect them. So I'd like to show you one example give you a flavor of how the synthetic things work if you're familiar with the classical atom spare sequence. So the E2 page is just a free polynomial algebra adding lambda. So classically, let's look at the first two non-zero differentials, which in this picture is going to be over here. Right? So that's the first Huff invariant 1 differential H4 supporting a D2 goes to the left by 1, go up by 2. Killing this element, the name is H0, H3 squared. And this is the non-zero D3 differentials H0, H4 killing H0, D0. So classically, when we go to the next page, the source and target disappears. That's the E3 page. Go to E4 page, then these things disappears. So in the infinity, they're all gone. But synthetically, H4 is supposed to kill lambda times this target, and D3 kills lambda squared times this target. So therefore, there are some leftovers, right? So we have the target has a single lambda torsion, and this is a lambda square torsion. So they are actually non-zero homotopy classes. So one way to think about this picture is that so each dot now is not just F2 anymore, it's F2 adding lambda. So lambda is detected by the homology point, therefore it has atom filtration 0. But you can think that as having atoms filtration -1. So therefore, for each dot, you think that supporting a lambda tower going down in here, that's a lambda multiple, and going down here, that's like a lambda square multiple, and so forth. And each differential will look exactly like a D1 differential, killing this dot times lambda, and the D3 will be killing this dot times lambda squared. So that's one way of keeping track of the gradings. Okay, and if we look at cofiber lambda, then all the differential will become 0 because lambda is already 0. So therefore everything survives, and the homotopy groups is just X. But if you look at sphere mod lambda squared, then H4 kills lambda times that. Lambda H4 kills lambda squared times that, which is already 0 because lambda squared is 0. D3 is still, well, D3 is always lambda squared times something, so it's always 0. And therefore, in this case, the elements that are the leftovers are, the target have a single lambda torsion, this has a lambda squared torsion, but moreover, the source also gives us a leftover. So these are actual information you don't see in the classical atom spare sequence, which you can make use of when studying, shuffling total brackets or, doing other things. All right. So having this idea, this sphere mod lambda squared, it encodes some information of the en+1 page. And then we can rigorously talk about differentials and extensions from another perspective. So now let's think about this cofiber sequence by multiplication by lambda to the n. So cofiber is of course that, and then we have the next term. So this boundary homomorphism actually encodes encodes all the atoms differential information, which we can refer this as a total atoms differential. So let's again look at this example, right? So n equals to 1, right? This gadget is just the cofiber lambda, so therefore its homotopy groups is just the x. So let's consider this element H4 is an element in X, but it's also homotopy class in here. It doesn't get to leave to the sphere because in sphere it supports a differential. So therefore, by exactness, it has to map to something non-zero over here. Okay, so what does it map to? Well, in here it's S mod lambda, so it's a single lambda torsion. So it has to map to something which is a single lambda torsion. This D2 differential creates to us a single lambda torsion, namely there is a homotopy class detected by H0, H3 squared, which is annihilated by lambda, and therefore we can actually prove that this delta 1, it sends this homotopy class H4 in here to this single lambda torsion H0, H3 squared over there. Similarly, if you're considering D3 differential kting lambda squared times something, then this element, which is single lambda torsion, will be sent to a lambda torsion here. Okay, and H0, D0 is annihilated by lambda squared, so therefore it sends to lambda multiple of that. So more importantly, these two D2 differentials, as you can see in the picture, the sources are connected by H0. There's a multiplication there, right? So that's a multiplication in X. Now it's a multiplication in the homotopy group of cofiber lambda. So that's showing that this total differential, so there is also a H2 extension between these two dots, namely the targets. So this dot times H0, it should be this dot times lambda. So they are leaving in the same degree. But here's a warning. Just like the classical case, whenever we talk about an element on the infinity page and the homotopy class is detected by it, there's always multiple choices. Every element in higher atoms filtration are in the indeterminacy. They are in the differences of any two such choices. So for example, if I take this element as an element in the infinity page, it's not in the infinity page classically, but now it is in the synthetic world. So the dot above it, like D0, so its lambda multiple will live in the same bigrading. So there are precisely two homotopy classes detected by this dot, and their differences is this element lambda D0. So therefore, the lambda D0 have this property that lambda D0 times H0 is precisely this dot. So that means that there are two choices for this homotopy class. One multiplication by H0 is non-zero, and the other one multiplication is precisely zero. So this kind of subtlety is very important when doing this kind of computation. It happens classically, it also happens synthetically. So if one is careless, it's very easy to make mistakes. So later on, for all the arguments, whenever we talk about the homotopy class, we have to be very specific about which class I'm talking about and the corresponding relation, because it may not be true if you're taking another choice. All right, so having seen these examples, you can imagine make a rigorous definition about extensions on the atoms EM page, and also being able to translate differentials to extension problems. So by setting up some very strict rules, such as strict conditions such as no crossing differentials, we can state some general rules called generalized Leibniz rule and generalized Mahorter trick. So
before you move on to the next thing, I'm going to check that it's correctly. So both this D2 differential and the D3 differential are encoded in the delta 1.
yes,
They're both seen by the same
Same delta 1.
sequence.
yes, same cofiber sequence.
So
Yes.
the delta n knows about differentials of all lengths.
Delta 1 knows differential of all lengths. Yes. Yeah.
Up to-
For different n, you can adjust. You can also add in more mod lambda to the n, mod lambda to the m, and mod lambda to the n plus m to play with, depending on your situation. So later on, you'll see in my talk, I'm going to be dealing with something like lambda to the 9, lambda to the 14, or things like that. You have to pick your choice to make these ad hoc arguments.
When you say delta n sees all differentials, you mean up through dn plus 1?
Delta n, no, but I mean delta 1 sees all the differentials as long as they survive. right? So when n equals 1, here is x. X have all the elements. Yeah. So I'd like to mention that to say these rules and this trick, you have to introduce something called low crossing differential conditions. That's precisely to avoid this kind of choices, to make a mistake. So actually, if we first actually stated some rules without the no crossing conditions, and we plug into the computer program, it gives us a contradiction like very quickly. So we have to add in more conditions to make sure there's the choices are correct. All right, so now I think I'm ready to talk about the inductive approach. Okay, so first to fix a few notations. For x, an element which is the permanent cycle, we use a curly bracket to denote the set of all classes detected by x in the infinity page, and the square bracket x to denote a specific or a general class in here, depending on the context. Let's see the 5 to denote a synthetic homotopy class detected by h5 squared that lives in this by degree. And I'm going to abuse notation to denote also by theta 5 all its images in this S mod lambda to the R. So eta will be the class not divisible by lambda, it's just detected by H1. And there's the fact that all the theta 5 in dimension 62 synthetically have order 2. So this follows from two facts. First of all, if you look at the bi-grading where this twice theta 5 lives, it does not contain any lambda torsion, and this can be simply read off from X information. So let me do that. So this is the X. So this is theta 5, right? So it lives in this by degree 62 and 62 comma 62 plus 2, right? The actual degree is just the t degree, the total degree. So so you see that in featuring 0 in 63, there's no dots in here. But suppose there is a dot, right? Supporting a D3 differential killing this dot. Suppose that's the case. Then this dot will have a leftover, which is a lambda square torsion, which means this dot will still be there. Its lambda multiple will still be there, but not its lambda square multiple, right? So then if there were this D3 differential, then this differential will create a lambda torsion that lives in the same by degree as theta 5. But since there's nothing like in here, there's only dots above, these differentials all above, they're not going to create any lambda torsion in this by degree. For example, this D2, it creates a single lambda torsion in this by degree. This, like a D3, it creates a lambda square torsion but lives in higher degrees. They're not going to interfere in here. So therefore, this by degree, it does not contain any lambda torsion. It's only lambda free elements. So that's the same information as the classical information. So classically, I proved that there exists a theta 5 has order 2, and Isaacson, Wang, and myself proved that every theta 5 has order 2, and therefore every synthetic theta 5 has order 2. Okay, having that in mind, so now I can state the inductive approach. So the theorem states that the element H6 squared survives to the ER plus 3 page of the classical atom square sequence. That's a completely classical statement. If and only if synthetically there exists some theta 5 such that this relation is 0 in sphere mod lambda to the R plus 1. So this is the same R as that R. And in particular, H6 is a permanent cycle classically if and only if for some theta 5 this expression is 0 in the synthetic sphere. So this is implicit in the statement that this expression for any choice of theta 5, they all agree. Okay. So the point of this upgrades in the synthetic setting is that not only this can tell us whether or not H6 is a permanent cycle, it should also be able to tell us if it does not survive, then which differential it should support. All right, so here's an idea of how we prove this inductive approach in the synthetic setting. So take any theta 5, it has order 2, so therefore I can extend it to the mod 2 Moore spectrum. Then I can consider the quadratic construction, and here are some pictures. So I take a theta 5 that has order 2, so I can have a mod 2 Moore spectrum extending this map. Then I plug in the quadratic construction. So classically, for a sphere, the output is a suspension of the standard projective space. The mod 2 Moore spectrum is going to be 2 copies of that, with an actual cell with some attaching map, then I just look for the a subcomplex which has these three cells. So the numbers instead of this square are the by degrees of the cell. Okay, and classically, so synthetically, we just whatever the output is, its underlying topological space is the same as the classical one. We just have to adjust the actual grading and also the lambda power in the attaching maps, and this turns out to be the answer. Okay, so having this picture, so classically, due to the Hopf invariant 1 solution, the non-homotopy of twice theta 5 is H6. So, and classically, the non-homotopy for this map from the middle cell is H6 squared and H7. So you can already see that classically, if theta 5 exists, twice theta 5 is 0, so namely this map exists. If also theta 5 squared is 0, then this map from the 3-cell complex to the single cell, because the bottom cell, the map is 0, you can get a map from the top to this sphere, and its restriction to the bottom cell has to be theta 6. So classically, if you know theta 5 squared is also 0, which we do not know at this moment, then we can conclude that not only theta 6 exists, but also twice theta 6 is 0. Okay? But we don't know if theta 5 squared is 0 or not. And also classically, you can read off for free that eta, but lambda goes to 1, so eta theta 5 squared is always 0 automatically. So synthetically, lambda squared eta times theta 5 squared is automatically 0. So the question is really about you reduce the power of lambda by 1, whether or not lambda eta theta 5 squared is 0. If that were 0, then theta 6 is a permanent cycle. If it's not 0, it's detected by some element in the Adams E2 page, say by Tn. We have to adjust the power of lambda to make the degree right. Then it gives us a non-zero differential like this. Okay? So this method also tells us if this product is non-zero, is detected by some element in the Adams E2 page, it gives us a non-zero differential of this expression. All right, so now that's the sketch of the inductive approach. So now it's our strategy to actually proving theta 6 as a permanent cycle. So as I mentioned, if this product were detected by some element, so classically this product has always been 0, but synthetically it could be detected by some lambda torsion, namely the target of some differential. Then there's the synthetic Adams differential, namely it's precisely this differential could create a lambda torsion and making this element still non-zero. So the goal is to steal the old-fashioned way of doing an Adams filtration estimation of this expression. So we start with theta 5 squared. So that's in dimension 124, and it's supposed to live in this bigrading plus 4. So then we look at the picture. So again, if we know theta 5 squared is 0, then that's a very straightforward direct proof. But you see that it's supposed to live in filtration 4, but there's nothing in filtration 4. And moreover, in dimension 125, there's nothing in this lower filtration. So similar logic tells us this element synthetically it lives in a bigrading of a group that does not contain any lambda torsion. Okay, then we don't have to look at for all the differentials, and we can just look for the leftovers. If you go to the infinity page, 124, there are still a bunch of dots, right? So the one which is of lowest dimension filtration is in filtration 10. It's this element has a name H0 squared x 124.8. So by inspection, the atom filtration has to be at least 10. And if it were to have filtration 10, then it's precisely detected by this element. So by the way, when we didn't have this synthetic technique and put it into the computer program, in this filtration 124,10, we still have like 4 dots. Okay, so there's still like a lot of possibilities and some linear combination, but afterwards it's only down to 1 dot, so it's much easier to deal with. Okay, so we do not know if theta 5 squared in particular is detected by this dot or not, but let's assume maybe at least this filtration, right? So next we estimate its eta multiple. So by inspection, we see the filtration has to be at least 14, right? So there's a dot in filtration 11, but on X it's not H1 multiple, so it has to jump filtration. Of course, we have to deal with all the lambda torsions, but for just for the sketch proof, it turns out this lambda torsion doesn't matter. And the one, which is the next one, is infiltration 14, is this element called H1, H4 something. Okay. So if it were have element filtration 14, and it has to be detected by this element. But if it's go even higher, then you can conclude that it is actually 0. So if you go up, you see that in 125, there's nothing left until filtration 25, and there's no more above. So in 25, you see that there are still 2 dots, but that's okay. So the right-hand dot is detected by TMF. So theta 5 is not detected by TMF, so therefore E to theta 5 squared has to be 0 in TMF, so therefore it cannot be detected by this right-hand dot. So left-hand dot, so this dot, the web page shows that D4 is not known, but the computer program actually knows a little bit more. It knows that this D4 is non-zero, but it couldn't decide whether it's the left dot or the sum of these 2 dots. Okay, so that's actual information which you cannot see from the web page, but it is in the data. So in either case, it shows us either the right-hand dot survives or the sum of these 2 dots survives. And in either case, the remaining 1 dot is detected by TMF, and therefore it cannot detect this product. So therefore, the only possibility is this dot in filtration 14 of stem 125. So in summary, what I have showed you, explained to you, is the following theorem, that exactly one of the 2 possibilities is true. Either theta 6 survives, or there is supports a non-zero D12 differential, killing this very dot in filtration 14. And the second possibility is true. This non-zero D12 differential happens if and only if 3 conditions are true. So I have already mentioned this existence of theta 5 squared detected by this dot in filtration 10, and this eta extension, namely that detects theta 5 squared, and there's an eta extension goes to this dot. There's another subtle possibility that in order to detect that, this dot has not been killed. It's a permanent cycle. It cannot be killed by any dot, any shorter differential. So you have to go back to 126, but in higher filtrations. You see that if you click on this dot, it's a permanent cycle. Click on this dot, it's a permanent cycle. Click on this dot, it says D6 is unknown. So that's the non-zero possibility we do not know. If there's a non-zero D6 killing the dot in filtration 14, then that's a much easier argument than that theta 6 survives. But we do not know that. Okay, so we cannot rule this out. So maybe when we plug in more finite spectrum and other maps, it could give us this D6 differential, then that's a much easier argument that theta 6 survives. And this D17 goes to 25. This is D18 goes to 25, so they do not matter. In particular, they cannot kill that dot. This one, again, the computer one says D3 is unknown, but we actually know this is non-zero. If you just go to the E3 page, you see that its H2 multiple supports a non-zero D3 differential. So this one has to support a non-zero D2 or D3. It cannot be a D2. It has to be D3. It's just that it should be this dot or this dot plus the dot on the right. So it's the one of the 2 possibilities. But in either case, this dot supports a non-zero D3, and therefore it's irrelevant to this argument, and one of these 2 dots have to go, or their sum. Okay, so in summary, theta 5 squared, the worst case scenario is non-zero detected by this dot. And another worst case scenario is there is the eta extension between these 2 dots, and that will give us a non-zero D12 differential. And if we can rule out any one of these possibilities, we know this D12 cannot happen, and therefore theta 6 survives. And so by the way, I mentioned that whenever I write a square bracket of theta 5, there's also always possible to involve a bunch of possibilities. So there are actual arguments one have to do to argue that in these expressions, these possibilities, they do not matter. Okay. So the way to prove the final theorem is to establish one of these 3 are not true. So we're going to assume 3 is 2, but we're going to prove that 5 is not true. Namely, this eta extension cannot happen, and therefore theta 6 does not survive. So for the sake of contradiction, we're going to assume 3 and 5 are both true and prove a contradiction.
Both B and 5 were
But
You just-
3 is this D6, 2 is not cubed by a shorter differential, 5 is this eta extension. So maybe it's easier for me to explain this in the picture. So that's the possible candidate for theta 5 squared. That's the possible candidate for eta, right? So we're going to, in the end, establish that this eta extension cannot happen, okay? So the way to prove this is the following. So you know that the source is also there's an eta, right? So if we have an eta square extension, there are some total bracket we can shuffle, right? But then the problem is this dot is not a permanent cycle. It only survives the E12 page. So later on, we're going to make an argument on S mod lambda to the 9 for some technical reason. And so that will be a homotopy class in that page. We're going to further prove that this element on that page has order 2. So whenever we have something that has order 2, its eta square multiple is non-zero, then this eta square multiple is always divisible by 2. So that's just a shuffling of a total bracket. So if this element were divisible by 2, you see that there are these 3 possibilities. I mean, there's always some lambda torsion we have to also take into account, but it turns out they are not relevant for this proof. So we can rule out the later 2. I mean, one of them is gone by killing by D3. We can rule out the other one and to show that this has to be the only possibility. So therefore, having this eta will force a 2 extension among these 2 dots. Then we see that in the cofibrock of nu, there is a differential connecting these 2 dots in cofibrock nu, meaning that there is a new extension through the generalized Mahorra trick. There's a new extension from this dot to this dot. Then combining, this is an independent fact. So combining this new extension with this 2 extension, we establish 2 new extension, which is also a first times 2, then times new thing. Then one of these 3 dots has to accept the 2 extension and go to this dot where a new extension. It cannot be this dot because there's no H2 multiplication on the E2 page. So it has to be one of these 2. So one of these 2 has to support the 2 extension or the sum, and then support a new extension goes to this dot. Then again, we read from the covariant nu to see that this dot in covariant nu is not cubed by a short enough differential to create this new extension and therefore reach a contradiction. So that's basically the ad hoc argument that took us like 10, 15 pages to do this. So what I said can be summarized to 4 lemmas. So I like to just to not go through the details, but just to show you the flavor of these statements. And these 4 lemmas together proves, is precisely what I just said here. Okay. So first I go for this alpha 1. So that's this element in here. So I want to use this H1 multiplication, right? So eta times alpha 1 is detected by this element, but know that 2 homotopy class detected by the same element, it doesn't mean they are the same in homotopy groups. It only means they're differed by possible higher filtration elements. If you look at this eta multiple and this theta 5 square, which is presumably detecting in here, their difference is goes to filtration at least 13. So that's why their difference alpha 2 lives in 13 in here. For this alpha 2, we know that in X, its H1 multiple is 0, so therefore a times eta is further divisible by lambda. We can also check that in lambda to the 9, this alpha 1 is annihilated by H0 and lambda cube. So this is the element alpha 1. It's not a permanent cycle. It leads to the E12 page, but in particular leads to S mod lambda to the 9, and you can prove this relation. I'll say something about how we actually prove this relation, but that's one lemma. And then, since we have this relation, we can define a synthetic total bracket. Okay, so that's precisely the total bracket that we are shuffling. So from this element, comma 2 essentially, then comma eta. So that should live in somewhere in here. That's the element. It's eta square multiple, then further divided by 2. So I claim that it has to be this dot, which is this element, x0 squared 125 9, 2. So that's the name of the dot. Okay, and then a corollary is that then there is a 2 extension from this dot to that dot. This 125 9, 2 times h0 is this top dot in filtration 14. It tries for this potential target of the D12 differential. And finally, using the generalized Mahorov trick, we can establish a new extension from this dot, H1 X121 7 to this dot in filtration 11. Okay, so having these four lemmas, we can give a sketch proof, right? So we can multiply by nu, then H0, and that's something here. Knowing that D6 is non-zero, we know this target is non-zero. Even if there's a non-zero D12 differential, it's just getting lambda to the 11th power, but lambda to the 8th power is still non-zero. So in particular, this product times H0 has to be non-zero. Namely, there's a new extension, there's two extension, A times 2 has to be non-zero, then A times nu. Then we look for all the possibilities. There are two possibilities in filtration 11 and filtration 12. That's these two dots I'm talking about. But then you realize that all this shuffling is in S mod lambda to the 9, but these two elements are actually permanent cycles. So they can be lifted to the synthetic sphere, not mod lambda to any power. And in both cases, this new extension can be lifted to this product in the sphere without on any page. But then we look at for covariant, so that implies this lambda to the 4th power is a multiple, means that this element from the bottom cell in covariant has to be killed by a differential at least 5. And then let's just check that's not the case. If we go to covariant, so this is an element in 125, 14. Okay, you see that there's a dot here. Maybe let me remove the dash so there are less. Oh no, dash 9. Right. So there are 4 dots in 125, 14. So that's the dot, right? From the bottom cell 0 and H1, H4, X1, 29, 12. So we need to know that this one is not killed by any differential up to length 5. So these are dimensions that could support a D2 killing that, but D2 are all known, right? And in particular, we know the fate of all these 4 dots. Okay. And for these 4 dots are the possible ones to support the D3. This one, D14 is unknown, so it's irrelevant. This dot is permanent, so it doesn't support D3 killing that. And these 2 are all targets, so they're permanent cycles. These 3 could support D4, but they are all accounted for. And there are 5 could support a D5. These 4 are accounted for only the middle one. The middle one, when I click on that, we do not know D16, so therefore it doesn't support a D5 killing that. The interesting thing is it's very sharp, right? If you go to the next page, there's our next filtration, there's already a D6 that we do not know, but that turns out to be the same as the one in the sphere, so that's expected. So anyways, so this can be checked, and therefore we have the conclusion. So as for contradiction, so as for the proof of the 4 lemmas, so if you're familiar with how to do these things classically, you can just do this synthetically with the extra care of the extra grading and all possible choices of homotopy classes, and then delicate atom filtration estimation. You can do that. A lot of the things are okay. When we shuffle, we have an atom filtration estimation. There are so many possibilities. We just have to give an ad hoc argument to rule out other possibilities, and the one remaining has to be the case, this kind of argument. And so that's the H2 multiplication, that's the generalized Leibniz rule, namely, we want to argue for a new multiplication. We started covariant nu, and there's a long sequence on X groups. Then we translate the differential in the covariant nu into a homotopy relation in the boundary homomorphism with some no crossing condition. We have this Mahorov trick to give us what we wanted. But another subtlety here is that the thing we wanted to argue is in S mod lambda to the 9. This conclusion is only work for S mod lambda to 3. We have to lift it back to S mod lambda to the 5 and push it where another map in order to get lambda to the 9. For each, to apply either map, by naturality, there are potentially a few more elements in the relevant dimensions that we have to rule out so they do not interfere with this relation, and that can be checked. All right, so in the last 5 minutes, I'd like to say a little bit about maybe what's next. So as we know, the atoms one line are generated by these classes Hj, And Adams proved that the first few survives and later on they do not. So that corresponds to a topological fact that the tangent bundle of the sphere is trivial if and only if only the first few have a tangent trivial bundle, have a trivial tangent bundle. So the covariance is for hj squared, and only the first few survives. The later ones they all die, and that corresponds to this free manifold with covariant invariant 1 statement. So so one open question here is, of course, what are the explicit differentials supported on the later ones? Because they could also give us some other homotopy theoretic meaning for, like, what should we expect for the large range patterns of differentials in the Adams sphere sequence. So one possible approach is to do this. Where's the sphere? And you know, just go to 254. As you can see, we already have a lot of like partial information, right? But there's a lot of, oh, this is D2 because the D2 program doesn't run this far. But there's a lot of like partial information, right? This one, I guess we know theta 6 has order 2. We can prove using other methods this is a permanent cycle, but the program doesn't know D4, right? And we know a lot of partial information, a lot of partial differential, but we're, you know, at the edge of this. So presumably, I do not expect the computer program to give us a differential, but together with this inductive approach and some ad hoc argument, it's possible that one can actually find an explicit differential of h7 squared, and then inductively maybe that allows us to produce differentials for later covariant classes. But the thing I really wanted to talk about is this square zero family story. So Brooklyn and I proved that a similar question you can ask for hj cube. The answer is only the first few survives, the later on they all die. But what would be an interpretation in terms of manifolds, free manifolds? So there are some theory developed by Miller and Laus and other people that instead of taking the resolution using HF2, we can use MO, the unoriented cobordism, right? So it splits as Vector suspension of HF2. So when we smash them together, the homological algebra are the same. It gives us the same X. So therefore, for any element in the X, or even differentials in the Adams sphere sequence, we could possibly interpret that into, that's like a map into, the E1 page is like a map, a sphere map into MO smashed with itself several times. It could be interpreted into manifolds with corners, right? You have a manifold in dimension n, you have, say, two manifolds of dimension n plus 1 with the same boundary, then you have a manifold in dimension n plus 2, whose boundary is the union of that, you know, things like that. It's possible that you can try to interpret this into the theory of free manifolds. For example, then this result would be trying to say that only there are free manifolds with certain structure, the certain is still unknown, that only happens in the dimensions when this hj cube survives, which is 3 less than 3 times the power of 2. So that could be something to, so in particular, in the half invariant case, it can be translated into, if you take an n-dimensional manifold with one layer, with an n plus 1 dimensional manifold having it as a boundary, you can translate the half invariant as the Stephen-Whitney number of the manifold in dimension n plus 1. You can also translate the covariant invariant into some product of the Wu numbers, some other characteristic numbers, which has the same value as the covariant invariant one. So it's possible maybe one can do more things and giving some translation for hj cube as well, or even for more general things. So, I mean, hj to the fourth power is 0 in X, but the good story is there are more things to be considered here. So there's an operation called square zero in X. It preserves the filtration, it doubles the total degree, in particular since hj is the next one, hj plus 1, and so are the squares and cubes. So we can define something called the square zero family by taking an X and the iteration of square zero. They're all in the same filtration. Then there is a new doomsday conjecture stating that within any non-zero square zero family, only finite many of them survives. Okay, so the hop covariant are two such examples. So in fact, the filtering 1, there's only the hop invariant family. In filtering 2, there are many classes, but for the square 0 families, they're essentially equivalent to the covariant invariant problems. Most of them just support non-zero D2 differentials. And for filtering 3, HD cube is done, but these are the only remaining cases. And other things are, we know the fate. There are the C family, they all support D2 differentials and other ones. So this threefold mass support on the E3 page, these are the only remaining cases when we fix the J and let K vary. For different K, there's a different square 0 family, and we do not know the fate of these things. But the expected answer is only finite many of them survives. And moreover, we have a conjecture stating precisely how they should die. Namely, there should always be two such families, and the fixed length, in particular, the length should stabilize when this J goes to infinity, which is true for all the known cases. So I think a very interesting question would be, for any such square 0 family, if there's an interpretation in terms of this frame smooth manifold with corners, then each family should tell us there's some structure of the manifold which only exists in certain dimensions. And if the new doomsday conjecture were true, then that's saying that only finite of these dimensions could have these families. All right, I'll stop here. Thank you.
To what extent are you able to do systematic automated consistency checks for these calculations?
That's a great question. So other than, I think there are a few groups of people are trying to do this. So one is the group, Dan Isaacson and his folks at Wayne State. They're trying to apply Wayne's program and to track this in, I don't know exactly how they would track it. I've been reached out by people trying to use some formal language like Lean to like formalize some of the things, which is not something I'm super familiar with. But I think they're all in progress. My take is that during the process of adding more features, how the program, we want the program to do, like compute Lami's rule, compute like a generalized Mahover trick, in the process of adding more modules, whenever we make some subtle mistake, it always gives us a contradiction like really quickly. So in some sense, the whole atom source sequence of the sphere, and together with a lot of other modules and all these maps, is very rigid, right? If you make a mistake somewhere, then 20 steps later, there's a contradiction. So it's always like that. But it's not like perfectly this way. Otherwise, you should be able to exhaust all the possibilities and prove all the differentials, right? So, but what the program knows is maybe there are certain possibilities. That's why there's no contradictions, right? That's the part. Yeah, that's probably the the only thing I can say.
In my experience with computer programming, so just because the program compiles doesn't really
Right.
prove that it works, but it's
Yeah.
using the wrong
I mean, another thing is like the features we're letting the computer programs do to us are the relatively like easy ones, right? Like, I mean, the way to produce D2 are not that easy, but to compute Lami's rule, that's supposed to be easy, like humanly trackable, right? So somehow I think historically, as you know, there are many, in the literature, many like errors and something doesn't match. I think usually, at least the thing I learned from Mahored is that, he always gives you another proof. So the way he gained confidence is, if you don't see it this way, you give other perspective. So altogether, you gain confidence, right? This is definitely not the way we're doing here, but I would say the relatively simple things are done by computer. Like nowadays, we all trust programs to compute E2 page for us, right? I don't think anyone is doubting. Like we're doing all kinds of like computations, like computer computes E2 page for us. We don't compute this part of the homological algebra by hand anymore. So it doesn't mean it's necessarily easy, but it's more routine in some sense.
So the ad hoc argument, at the moment you presented that sort of a sequence of steps, but if one could somehow merge them better together, then maybe that would also be a kind of consistency check. So what I have in mind is you
Right.
mentioned that if you have a class of order 2, then eta squared on it is always divisible by 2.
Yeah.
And you can describe that as shuffling, but you can also sort of take the sphere mod 2 as a universal example. If you have a class of order 2, then you can map the sphere mod 2 in.
Yes.
And if you're looking at a spectral sequence for the sphere mod 2, you see that eta squared is divisible by h mod 2. So you could somehow ask, is there a similar universal example, maybe mapping in, where also these various things about the 2 new and new 2, where a bigger part of your argument,
Right.
is there sort of a universal example mapping in to model a bigger part of your ad hoc argument?
So, well, we haven't really thought about how to, just for this part of the ad hoc argument, because it's only like 10 plus pages. It's not, but in general, I think V9 is trying to, whenever you have a spectrum, you have atoms per sequence, you look up on a point on the infinity page, it corresponds to multiple homotopy class. You can always find a way to figure out the distinction and use that as an attachment map to attach one more cell. So V9 has been trying to adding more finite cell complexes this way, right? But in general, it could be many finite cell complexes have the same homology over the single algebra or even over the secondary. So they have the same E2 on E3 page. Then the higher differential telling you they correspond to different homotopy types, right? So then whatever we're using, since we're undetermined are in some sense, it's not only for one spectrum, it could be several spectrum with the similar information like this. But V9 is trying to make a distinction, and but that's in the progress, to produce finite cell complexes this way, and then add into data and write all the natural attitude maps. If there's no contradiction, then you're good, right? You're supposed to be good, and just to keep doing this, like not by hand, but let the computer program to add in more spectrum here. So we thought about how many spectrum we want to involve at some point. So in the beginning, of course, we add in everything we could possibly think of. So it's like over 100. Later on, we realized maybe it's easier to track things if there are less spectrum involved. We get down to 49, but we haven't tried really hard to say, can we get it down to 10 or something? We haven't really think about that. I think maybe this is a good stage for double check.
Different kind of question. So the whole story about Zhouli Xu algebra and the BT star VP and so on is all kind of tightly connected with thermal groups.
Yeah.
Is there anything you can say about that in the synthetic framework?
I mean, it's this two deformation story I was mentioning, right? So both this synthetic and motivic, they are like enlargement of the classical category. That's one way to see it. They're like a bigraded spheres. So specific for the synthetic, you have this this deformation that this thing is generated by these bigraded spheres, but the modules over covariant lambda are this derived category of the. So presumably whatever. So for example, people studied all the non-nilpotent maps in here that can be translated to some synthetic chromatic story in here, but there are more to it because that's only a special flavor. So I think there are a lot of things you can study using these connections, or at least more questions you can ask.
Okay. Let's go right here.